All right, guys, Professor Burns here. Let's take a look at section 4.5, which is on a really important topic called optimization. If you are a science major or a business major, this is a topic that you would use to look at where there is a maximum or a minimum for some type of quantity. Maybe you want to know where a population reaches its maximum, or you want to minimize your costs. That's what this is all about. So make sure that your cell phones are put away and aside so that you can focus for the next few minutes and take good notes. I'm going to start with a classic problem here. This is one that comes up a lot in basic calculus courses. And it says you have 40 feet of fence to enclose a rectangular garden along the side of a barn. So I'm going to draw a little picture here. And I'm, as you know, a very terrible artist, but that's all right. We're going to pretend that this is my barn right here, and I'm going to put in a garden next to it that is in the shape of a rectangle, and as you can see, I'm a terrible artist. Let me try to straighten that up a little bit. So my garden is going to go this way. So it's along the side of a barn. So the thing to notice here is only 3 sides need to be fenced in. I have 40 feet, so think about what the units would be for that. 40 feet would refer to linear units, so that would be your perimeter. I have 40 feet of fencing at my disposal. Now, how much I want to maximize the area. The area is what I want to maximize. So what I'm going to do is I'm going to put some labels here, and I'm going to call this side X and this side Y. And then, of course, because it's a rectangle, this side would also be X. So I want to come up with 2 equations here, one for the area and one for the fencing or the perimeter. So let me start with the area equation. Area would just be length times width because it's a rectangle, so that would be X times Y. And then the perimeter, well, think about what that would be. That would be X plus Y. Remember what perimeter is. You add the sides together. There's only 3 sides, so I don't have to do anything with the side where the barn is. And that is constrained by the 40 feet. That's all I have. So I've got 2x, if I combine like terms, plus y equals 40 feet. My job here is to maximize this equation. The area equation is what I want to maximize. So to do that, when you think maximum or minimum, you think derivative, right? I want to take the derivative of this expression. And I don't want to take the derivative with 2 variables. So what I'm going to do is I'm going to substitute using my constraint, that secondary equation. I'm going to substitute for one of these variables. I'm going to solve, in other words, for either x or y and substitute that into the equation that I need to take the derivative of. I think it's easiest to solve for y, so I'm going to subtract the 2x. So I have 40 minus 2x equals y from this equation above. And I'm going to plug that in for y into the area of equation. So then my area equation becomes x times 40 minus 2x. Make sure you see what I'm doing here. Let me use the highlighter here. This expression was replaced or put in place of the y right there. I literally made a substitution for that. Now that my area equation is just in terms of one variable, I can take the derivative of it. Now I'm multiplying this x times this 40 minus x, so I'm going to distribute the x first before I take the derivative. So 40x minus 2x squared. So my derivative, a prime, would be 40 minus 4x. So to find a maximum or a minimum, I'm going to set this equal to 0, and I'm going to solve. So I get 40 equals 4x. Divide by 4, I get x equals 10. So my maximum should occur when x is 10. How do we verify that this is a maximum? We do our number line analysis, just like we did earlier in this chapter. I'm going to plug in 10 for x. If I check a number to the left of that as my test point, I get a positive value for a prime. If I check a number to the right, I get a negative. So when my first derivative changes from positive to negative, I get a maximum. So that means 10 is the maximum x can be and keep me within this 40 feet constraint. Now they asked for the area, so I'm going to go back and I'm going to substitute 10 in place of the area equation. Remember, area was, you can do 40x minus 2x squared. So I've got 40 times 10 minus 2 times 10 squared gives me 400 minus 200, which means my maximum area is going to be 200, and that would be in square feet. And that's it. So an optimization problem, the goal here is to find an equation I can take the derivative and get the local maximum or minimum using the first derivative test. So a couple of steps here that might be helpful. Make a sketch if it's helpful. It's kind of like we did related rates. Sometimes it helps, sometimes it's not necessary. Write down all of the known quantities if they gave anything to us, like the 40 feet. Write down the quantities that you want to find, and then write down the equation for the quantity that is to be maximized or minimized. So I'm going to call that, actually I think our book calls that the primary equation. So let me write that down. So write down the primary equation. I'm abbreviating equation, and that's what you want to maximize or minimize. In the last example, my primary equation was the area equation. If you need to, rewrite that primary equation using a single variable, or as a single variable using a secondary equation. So the secondary equation in that last example was the perimeter equation. So let's make a note that this was my primary equation, and then this equation was my secondary equation. Now, not all problems are going to have two equations. You only need both equations when there's more than one quantity in that primary equation. We'll see some examples of both. Determine the feasible domain if necessary. So in other words, numbers can't be negative, for example. If you get a negative result or a negative value for your max or min, we would throw that out. So just consider what would be reasonable or feasible, and then find the max or min by using calculus, and we'll make a note that we'll use the first derivative test, and that's what we did. All right, let's look at an example. Find what dimensions for a 1 liter cylindrical can will use the least amount of material. Assume the can is closed. Now we're talking about some geometry formulas here, and if there's any specific geometry formulas you need, I will give those to you, so don't worry about that. Let's focus on the process. I'm going to draw a little sketch here of a cylinder, and it says assume the can is closed. That means it's got a top and a bottom that are identical. We would have a radius that looks like this, and a height for the can that would look like this. And we want to find the dimensions, that's the radius and the height, for the can. And so it needs to be 1 liter. Well, think about liter. What measurement would that refer to? That would be a measurement of volume. So the volume for the can needs to be 1 liter. And we want to use the least amount of material. When you see words like least, most, greatest, smallest, biggest, things like that, extremes, that's when we're talking about maximum or minimum, and we're talking about optimization. So this means we want to minimize. And what is it we want to minimize? We want to minimize the amount of material. So that would refer to the surface area. How much material are we going to take up in square units? So one thing I think might be helpful in this problem, I remember doing this problem before, and one thing that might be helpful in this problem is to consider the units a little bit here. Normally this will not be something you need to worry about, but just to make the work here a little bit easier, 1 liter, and I just looked this up, 1 liter is equal to 1,000 cubic centimeters. So what I'm going to do, instead of saying 1, I'm going to say the volume is 1,000, and we're going to use cubic centimeters for the unit for that, which means that my surface area will be in squared centimeters, because we're talking about area, that's square units, and centimeters make more sense to me. So let's go with this information. Now let's get some formulas here. So what have I done? I've written down, I made a sketch, I wrote down the one known quantity, which was the 1,000 square centimeters. I want to minimize the surface area. So let's write down the primary equation. So the surface area, I'm going to just call it S for surface area for a cylinder. Now you may not remember this, and don't worry about it. It's not that big of a deal, but it's the area of the circle. So that's pi r squared times 2 because there's 2. There's one on the top and one on the bottom. So 2 pi r squared plus, and then think about the label around the can. Like if you had a can of soup or something, the label around it would be 2 pi r, so the circumference of the circle, times the height. So 2 pi r times the height. That's what we're going to minimize. Now, I also need, because there's two variables, radius and height, I need to rewrite this using a single variable, which means I need a secondary equation, and that's where the volume comes in. So the formula for the volume is going to be pi r squared h. Again, do not worry about it if you don't remember where I'm getting that from. It's not a big deal. I'll give you the geometry formulas. Focus on the process here. This would be equal to 1,000. So that's my secondary or my constraint equation. So I'm going to solve for a variable here. Which one seems easier to solve for? Well, let me ask it this way. I think it's probably easiest to substitute for h. So I'm going to do that. I'm going to have h equal 1,000 divided by pi r squared, and then I'm going to substitute that into my surface area equation. And I'm short on space. I don't know why I made this so short in my notes. I'll adjust that for you guys when you get them. So I'm going to substitute that in though. We've got 2 pi r squared plus 2 pi r times h now is 1,000 divided by pi r squared. And this is not the prettiest equation, but this is an equation we can take the derivative of. I'm going to simplify a little bit. I'm going to cross out this pi, and I'm going to cross out this r with one of these r's. So now I have 2 pi r squared plus 2 times 1,000, so 2,000 over r, which becomes 2 pi r squared plus 2,000 times r to the negative first. Now let's take the derivative. We get s prime would be 4 pi r minus 2,000 r to the negative second. And we want to set that equal to 0. We've got 4 pi r. I'm going to move that 2,000 term to the other side, so 2,000 r to the negative second. And I move it back to the denominator, so we get 2,000 over r squared. And then I'm going to cross multiply, so I have 4 pi r to the third equals 2,000. Boy, I really didn't leave you enough room here, so let me come back up here and write. I'm going to divide both sides by 4 pi. So I have r cubed equals 2,000 divided by 4 pi. Now I'm going to take the cube root of both sides, and I'm going to put that in my calculator and get a decimal for that. Because this is a practical kind of situation, I think it makes more sense to do that. So I'm to get a decimal answer. So I'm getting 5.42 centimeters. Now, they asked for dimensions, so I do need to go back and get the height. Don't forget, though, height was equal to 1,000 divided by pi r squared from our secondary equation there. So my height would be 1,000 divided by pi times 5.42 squared. So let me get that number from my calculator. And I'm getting a height of 10.84 centimeters. So these are the dimensions that will minimize the surface area, but keep my volume at the 1,000 cubic centimeters. If we were really being thorough about this, we should do a number line analysis and verify that this radius actually does give us a maximum. But if it's the only critical number you get, you can pretty much rest assured that that's going to be it, unless it's a really complicated problem for some reason. And that's what's noted here in this important points section. And so we'll do some practice with this in class tomorrow, so I'll see you then.